Alrighty. Hello, everybody. So this is a history lesson type of talk. If you're relatively new to Kubernetes or to cloud-native technology in general, most of this is going to be new. If not, unless the history of computing is your special interest or you're over the age of like 80-ish, you are still going to walk out of here having learned something new. Something cool about how we got from something very old to Kubernetes. So Kubernetes is the solution to a 60-year-old problem. We've been trying to solve this problem over and over again for decades, and we will probably keep trying to solve it and never really get there, but this is where we're at right now. And it's indispensable in situations where it's useful, but it is undeniably complex and often can be kind of difficult to use. And we tend to try to chalk that up to its newness. There's a lot of, well, it's only on 1X, it's still new, it's still a baby, but it was publicly released in 2014. It's more than a decade old at this point. And it's not as bad as it used to be. We have built more tools on top of Kubernetes that reduce its apparent complexity, and we've done this to every other piece of technology that shapes the way we interact with computers today, to make it more palatable for people that don't shift their entire careers to learn whatever the bleeding edge is. Eventually, we'll end up with some kind of abstraction layer that does make it totally painless to use, but right now, it's still going to have this reputation for being hard. And this isn't a uniquely Kubernetes problem. CI/CD has the same issue. We like to say that feels new, but its origins predate the concept of DevOps pretty significantly, by more than a decade. Infrastructure as code also feels very, very new. Platform engineering feels very new, but we've been programmatically defining how machines behave, how fleets of machines behave also for decades. It is a marketing thing. What's going on here is that we are like over and over and over again solving the same technical problem flavored by whatever pain point of the time makes an issue unignorable. It's always just slapping an abstraction layer on something. Kubernetes is absolutely no different. Since the dawn of virtualization, we have had problems with workloads and scale. This is not new. So for those of you who do not know who I am, my name is Cosgrove. I will rattle off some Kubernetes credentials, but that's my actual job and how you can get a hold of me. I'm a technical lead for SIG docs within the Kubernetes project. I own the release team sub-project. I was the release lead for 130, and I'm currently a member of the Kubernetes steering committee. So I actually have a note here on my slide that says, don't forget your fancy titles, because the last time I gave this talk, I did, and nobody knew who I was. So now you know why I can talk about this. So that was the logo for version 130, which was my release, Kubernetes. It's very, very cute. It made a lot of people on Reddit mad, which was a huge, huge career moment for me, pissing off a bunch of Redditors. But the downside of the way we build technology with this like slapping an abstraction layer on top of an existing piece of tooling is that the further we get from the origin of that whatever pain point caused that new class of tool to exist, the more we lose sight of what necessitated that change. And it makes things seem more difficult than they are. So like Jenkins seems hard and crappy as a CI tool until you try managing deployments multiple times a day by hand. That sucks. That's how we had to do things before we had tools like Jenkins. So yeah, Jenkins is kind of janky, but it could be so much worse. Terraform is confusing and fragile and brittle unless you have had to define and maintain infrastructure for dozens of wildly disparate environments manually. Kubernetes seems hard until you have to dynamically scale an application for hundreds of thousands of users without it. And virtualization seems like a lot of work until you try to accomplish that exact same task on only one machine, running only one thing at a time. So a quick note for anybody in the room who is new, a pretty common question you get when somebody is first learning to use containers in Kubernetes is around the difference between a virtual machine and a container. This is an extreme oversimplification, but it comes down to exactly what you're virtualizing. So virtualization broadly is the use of a computer to simulate one or more aspects of a computer. It's something we've been trying to achieve to varying degrees with varying degrees of success since very close to the dawn of computing, and we've gotten pretty good at it at this point. The three types of virtualization you're probably most familiar with are hardware virtualization, so a complete VM, desktop virtualization, so like some kind of remote desktop application, and containerization, which is just an operating system. Things like VPNs and distributed file systems are also virtualization, though, and Kubernetes relies on a lot of different types of virtualization to operate, so it owes itself to a very long history of us trying to do more with less. And here comes the fun history part. This is the ENIAC machine. This was owned by the US Army, and it was one of the first computers. In the very early days of computing, machines were enormous and extremely expensive. You did not buy one of these things. This was not something you could purchase. They were leased to you by the manufacturer. And it was not cheap at all. If you've ever seen the TV show Mad Men, there's a whole story arc where they get one, and it was a really big deal, and everybody was mad that it took up like the entire entryway of the office. But that's how it was. You rented these, and you would obviously want to get everything you could out of having this expensive monolith taking up most of your office. But these things could only run one program at a time. You wrote your program offline using punch cards or paper tape, depending on how old the machine is, and then you show up at the machine for your scheduled slot to run your one program, stand there and wait for the output, and then leave. Eventually, we did get the ability to run multiple programs sequentially. We called this batch processing. We still do this. You're all probably familiar with the term, or you've at least heard it before. But you're still standing there waiting for output. It still can't do multiple things simultaneously. It was still saving us quite a bit of time. We very rapidly went from being able to, somebody would take an entire lifetime, like their whole career, to solve a problem, to one of these computers being able to do it in hours. So that's pretty cool, but we were still looking for a way to do more. So in 1959, the first patent was filed describing a system that would allow for multi-programming, and we coined the term time-sharing. That is an IBM 7074. Still pretty big, but smaller than the ENIAC. A bunch of fancy universities, MIT, Dartmouth, and some others jumped on board, but the actual machines were too expensive. There were a lot of really extreme hardware limitations, and there wasn't actually a general purpose time-sharing operating system at the time. So batch processing remained the way things were done, even though we had the idea for time-sharing. So this like conceptual jump from batch processing to time-sharing is significant. It was a spark, and somebody did eventually bet on it. In order to implement time sharing, we needed an advance in computing that was still, unfortunately, very theoretical at the time, and that was virtualized memory. We didn't have virtual memory back then. Today, this is so ubiquitous that you probably do not even think about it, but the user or the application is given the impression, whether that's reality or not, that it has access to a large contiguous pool of memory. I know that sounds so simple, but this was an incredibly hard problem to solve at the time, and we would not have anything we have today without it. So this is the Atlas supercomputer being booted for the first time at the University of Manchester. And this was the first functional implementation of virtual memory. It was called one-store memory at the time. This machine was a joint venture between two companies called Ferranti and Plessey in '62. The OS it's running is called the Atlas Supervisor, and it is the origin of all modern operating systems, which is pretty cool. It used a memory paging technique to achieve this one-store memory, and we still do that today. So I think that's a fun little tidbit that we're still doing it this way in some applications. Ferranti did build two more of these systems, but they were never made commercially available. This was not something you could buy. These were research only. There was a derivative system called Atlas II, also called the Titan, that was built for Cambridge University, but it did not implement virtual memory and so does not count. Unfortunately, these computers are so old that there isn't a ton of documentation about them, and very few people left alive who remember operating them, which is unfortunate. You can go see the Atlas at the museum in Manchester, though, which is, you can go look at it, or at least you can go look at its control panel. But the Atlas was, without a doubt, one of the most important machines in computing history. So this is the System 370-67, maybe the second or third most famous computer in history. In the 60s, IBM started developing this series of mainframes. And unlike their previous product lines, the S360 covered a wide range of speeds and price points. It also prioritized backwards compatibility, which was not a thing in mainframes before that. Before this series, if you bought a new or leased a new machine, you also needed new printers, new punch cards. Everything had to be replaced. That kind of sucked. So going with backwards compatibility was unheard of at the time. It was a huge gamble for them, and I think it paid off. Not to be outdone by themselves, this is also the series in which they achieved full virtualization, including virtual memory. It was the first time it was available in a commercially available machine, and they also developed the CP40 operating system. That was the first virtual machine OS. By 67, the 360-67, paired with the CP67 OS, which was just a re-implementation of CP40, was available in commercial use. It popped off pretty much immediately. This release won IBM pretty much unconcerted dominance over the mainframe market. It was enough of a thing that the companies collectively that were making and selling mainframes were referred to as IBM and the Seven Dwarves, because it was just IBM at the top and then Honeywell and whoever else kind of fighting for scraps at the time. But this absolutely changed the trajectory of computing. Trajectory was a specific word choice because this machine is also what sent us to the moon. All of the computing for the Saturn V rocket, which I maintain is one of the coolest things humanity has ever built, was done on a 360-67 and the CP67 OS. So after several decades, this thing that's going to become Kubernetes, it sent us to the moon, which is sweet. Sorry, if you're ever in Huntsville, Alabama, for whatever reason, they have a Saturn V that you can go check out at the Space Center there. It is really cool. They also have a moon lander and some moon rocks that you can touch. So that's just saying. If you think space is cool and you're in Huntsville, Alabama, go look. Anyway. From this point in history, the virtualization problem is cracked and things start moving really, really, really fast. In 1969, development of the Unix operating system began at the Bell Labs location in Murray Hill, New Jersey. That is a picture of it. It is mostly not there anymore, which I find very sad because a lot of really cool stuff was invented at Murray Hill. This version was intended for use internal at AT&T, but the Unix we have today is based on that original 1969 version. And just 10 years later, in 79, Unix 7 included the first step towards containerization. And that would be the Troot call. I am willing to argue with people about how I pronounce that after the talk. So if you don't know what Troot does, it isolates a program and its children by changing the program's apparent root directory, which prevents it from being able to modify files outside of its new tree in most situations. This environment is called a Troot jail, and it's the first example of what we would eventually call a container. This is also where the virtualization timeline kind of begins to split. The development of classical virtual machines continues on. Obviously, we still see and use those today. They're still getting better today. They still have their own applications, but this is also the beginning of the path to containers. Things start moving very, very fast in the early 2000s. So FreeBSD decided to explicitly develop for this eventuality. They expanded support for Troot and introduced the jail command with its 2000 release. Unlike Troot, jail allowed for complete file system and root privilege isolation, stuff like CPU quotas and memory limits, and a whole bunch of features that anybody who works with containers today would recognize. At this point, everybody else jumps on board too. I had to cut a lot from this slide to actually fit it on a slide, but we got Virtuoso in 2001, Solaris did it in 2004, vkernel in 2006. I can't overstate how much of a feeding frenzy this was. There are literally like a dozen different things from companies you recognize and projects you recognize and some that you've never heard of that were all trying to do this within about like an 8-year stretch of time. Nothing was really taking off yet though. Like we had these tools, but it wasn't a trend. We weren't explicitly developing with them. It was kind of just like a weird nerds thing. Oh no. So prior to the ubiquity of cloud computing, provisioning computing resources meant getting new physical infrastructure, right? Whether that was going to actually buy stuff or calling up your local data center and adding another server rental to your account. The pay-as-you-go utility commuting model wasn't really a thing, so scaling to infinity was also not really a thing. It wasn't easy to do back then, and anyway, the only companies who needed or wanted to do that were like large multinational corporations. Some research institutions had like weird problems with scale that they had to deal with, but for the most part, this wasn't an issue for the overwhelming majority of companies, so there was no reason to lean hard on containers. But the threshold for what we consider to mean at scale changes a lot. It changes every time technology evolves. I hate the term scale. I don't ever want to see it used in a serious professional context if I can avoid it, because it doesn't mean anything outside of the moment in which you say that word. It could be something else a month later. So one day in 2006, AWS released the first version of EC2. And suddenly scalability became absolutely everybody's problem. EC2 and the general popularity of utility computing made it very easy for any small business to take up and pay for the exact amount of resources that they needed, but we didn't actually have the tools to do that well. We didn't have the tools to manage that infrastructure. They hadn't kept up with the rapidly growing complexity of applications built for that world. And also what exactly that infrastructure looked like was still in flux. We didn't know yet. So it was kind of messy time in computing. But things do tend to get weird in more than one way at a time. In 2008, the public release of C groups into the Linux kernel mainline. This had been in development at Google since 2006, but the public release was 2008. And this allows you to isolate and limit resource usage for a collection of processes. Most of the tools we use today directly rely on C groups, including Kubernetes, and we're currently deprecating C groups in favor of C groups 2. But this didn't happen immediately. In 2008, we got LXC, which some of you have probably used, and in 2010, systemd nspawn. Both of these were built on top of C groups, and we're probably at the point in the talk where I'm talking about tools that most of you have directly used. But nothing released so far solved the issue of portability or user-friendliness. Containers are useful. We know this at this point in the timeline, that they're good, and we want to stick with that kind of thing. Microservices as a concept were kind of just beginning to take off, but hadn't quite taken over modern software development yet. And just like the mainframes and the move from batch processing to time sharing, it is not just the technical hurdle that matters, it's how accessible that tool is. And I know that we all love to hate on Docker, but we do in fact have to give them a ton of credit for the way we build things today. It was released in 2013 and pretty much took off immediately. If you go look at the Google Trends history for Docker, it is in fact a hockey stick. It is straight up and to the right. It's really impressive how quickly it took off, and I think that that was due in no small part to its approachability. It made it easy to share containers through registries. They were small, they were well-defined, they were portable, they're great. I still prefer Docker over Podman, so sorry. Yeah, and now that we're all developing with microservices and chucking everything into containers like those engineers in the 60s sure wished they could, we have to look at virtualization again to solve another complexity problem. Just 1 year later, Google announced the first public release of Kubernetes with Docker as its first runtime, and the rest is our careers, at least mine and Nick's, and several other people in this room. So a whole industry has sprung up around, did I just hear somebody exclaim Jesus Christ at that? Yeah. Yeah. A bajillion startups, more foundations than anybody knows what to do with, more conferences than I can attend, including this one. We owe this entire ecosystem to 70 years of trying to solve the same problem. How do I do more of this, but faster? This isn't even the most recent CNCF landscape, y'all. I'm so serious. This screenshot's like 6 months old. If you go to l.cncf.io, it'll show you the whole thing. Yeah, and it's like, it's really, it's overwhelming. I can't keep track of it. Shout out to the Technical Oversight Committee for managing that so that I just have to use it as a dramatic punchline on a slide in a talk and not actually keep track of what's in there. Anyway, this is another picture of the Atlas II. Surprisingly difficult to find good pictures of that thing, but looking back at this machine, the first machine to crack the virtualization problem, it seems really, really primitive when you compare it to Kubernetes. Yeah, like, I mean, it's a big gray and green beige thing that kind of just does math pretty fast. That's all, right? But we're still trying to solve the same problem. We're always going to be trying to do more with less effort, more with less resources in a computing way, because it costs us less, because it's less bad for the environment, because, I don't know, we're, as humans, greedy by nature. So what is going to make Kubernetes in 70 years look like that? I don't know. What is this landscape going to look like in 70 years? Is the CNCF still going to exist in 70 years? I hope not. Don't die. Anyway, yeah, I think it's fun to take a look back at how these really, really complex pieces of technology have evolved over time, how we went from a computer the size of a gymnasium that can kind of just answer yes or no, to an enormous distributed system that requires large teams of several people being paid 6 figures just to operate. It's weird, especially when you try to guess at the way things will happen in the future. I don't think that any of the people working on the System 360 or the ENIAC machine would have been able to predict Kubernetes. So maybe it's pointless to try to figure out where we're going to be in 70 years and what's going to make Kubernetes look primitive, but it's a fun thought experiment. Thank you.
Thanks, Kat.
You're so welcome.
Yeah, it's really refreshing to see a bunch of stuff that happened before I was born. So we've got about 10 minutes for questions. If anybody's got any questions that they'd like to ask Kat about Kubernetes, pissing off Reddit. My introduction to Kat's work was the epic Deadbird shit postings of quite a while ago. So
yeah, I used to not be able to keep my mouth shut online. I thought every thought in my head needed to be on Twitter. Yeah.
Any questions?
I'll just ask questions about Kubernetes for hours. All the locals know we'll do this. Do you know what ingress controller the Atlas II was running? That was my little, warm everyone up. My real question is probably less related to Kubernetes, but Kubernetes is this huge open source project, really, right?
Second largest in the world behind Linux.
may have heard of that.
Yeah.
And so less Kubernetes specific, but I guess because you've been part of the release team and everything, if you could talk a little bit about the challenges of like operating within that on GitHub and that sort of scale, I think could be interesting.
Because we're so large, we do have to kind of function like an org in a company. So the release team is built up of 4 sub-teams. So one handles docs, one handles comms, enhancements, and release signal. Each of those has a sub-team lead. Each sub-team lead has between 4 and 6 shadows working for them. If you're interested in being on the Kubernetes release team, the Shadow application is an open thing. Anybody can apply to Shadow on the Kubernetes release team. You don't need to be an existing contributor to Kubernetes. You can just apply. I will warn that we get like 200 applicants for like 25-ish positions. So don't be surprised or feel bad if you don't get picked the first time. It does not mean that you're not useful or cool or we don't want you. It just means we have so many options and we have to balance for geo. So actually being in Australia is a benefit to you. So take a crack at it if you want. But each of those sub-teams handles different aspects of the release process. The docs sub-team is responsible for generating release notes and for making sure that every enhancement that has a user-facing change has that change documented. We don't allow undocumented user-facing features in Kubernetes. If you can interact with it, we have it documented. Which I think is cool and something more projects should do. Enhancements is responsible for making sure that any KEP, Kubernetes enhancement proposal, complies with all of our rules for things like test coverage, documentation, make sure that code PRs and test PRs are merged on time. Release signal is responsible for bug smashing and for just keeping a general eye on our test grid. And comms is responsible for things like interfacing with the CNCF PR team, enforcing media embargoes, scheduling interviews for the release lead, and making sure that any interesting features in the upcoming release get a feature blog. So there's a lot to do on the release team. All of those sub-teams report to a release lead that is a different person every 3-ish months, and that release lead reports up to me. So I'm just there to handle emergencies. Everything else day-to-day gets handled by the lead and the sub-team. But this is a team we put together 3 times a year. The next application for Shadows, I will open it in like late December. So if you're interested, join the Kubernetes Slack workspace and be in the SIG release channel, and you'll get a notification when I open it up. But do come. It's fun. It also gets you org membership automatically, which is it's probably the fastest way to Kubernetes org membership, because we do, release team members have elevated access to stuff. So you are an org member if you're on the team.
Thank you. Great presentation. 2 questions. So number 1, the slide you show all of the contributors, that's the shocking one, all of this out together, has been talked to having some sense of consolidation or certain brand merged together. Because if you're looking for the engineering, it's good to have it, work community, all of the other tools, but becoming too much to manage.
So no, we can't really force any of these to merge. So we keep them organized into categories of what they are, what does this project or this business do, but we can't force Helm and build packs to merge into one thing. They get to do whatever they want. The CNCF also, I don't work for the CNCF, so this is all has to be my opinion. But the CNCF has a policy of no king making. So they do not come down from on high and say, Helm is the way we're solving this problem, or Flux is the way we're solving this problem. By their very nature, they want people to have options, because all of these are slightly different too. Flux and Argo don't approach CD in the exact same way. They approach it in slightly different ways that are beneficial for one team, but maybe not for another. So, I don't know, it's overwhelming to look at, yeah, but I don't think the CNCF is ever gonna limit new, cloud native database tools or new, CI tools from being included.
Okay. And the second question is, what's the latest or your opinion about the Kubernetes 2.0 to just try to reduce the amount of maintenance, all of the crazy YAML files across any repo?
Sorry, what?
So what's the news about the Kubernetes 2.0?
Oh, okay.
About the reduce the amount of toil to maintain so many YAML files across the spectrum.
So I don't know when we're going to go to Kubernetes 2.0. I guess I would say that that's not my call, but now I'm on the steering committee, so it is actually my call. Well, it's our collective call. Do it. You know what? I'll ask at the next steering committee meeting, when are we doing this? But as for like things like reducing toil with a huge amount of YAML required to babysit, that's actually up to whatever SIG is responsible for that aspect of, would that be SIG node, Nick? This feels like a node-ish problem.
It depends on what you're talking about.
Yeah, like it's...
I'm making the problem worse with Gateway.
Yeah, like there's so many different, so like the Kubernetes project is made up of 35 different SIGs, and all of them are, not all of them, but most of them do stuff that can result in you needing to wrangle more YAML. So if there is an area in which you would like to see a reduction in the amount of YAML you're wrangling, then unfortunately I have to give you the very open source answer of PR's welcome. Like we're an open source project. If somebody wants it, you can come build it. But like we as a project don't like specifically have those kinds of overarching plans. We like reducing toil where we can, but the steering committee very rarely comes down from on high and says, y'all have to do this. When we do, it's like a security issue or like a weird people problem. The steering committee is not a technical leadership committee. It's a people thing. So yeah, if you think you got too much YAML in one area of your Kubernetes deployment, you go join that SIG and you go fight with them. Open a PR.
Thanks, Kat. Great presentation. I got two questions. So I heard Kubernetes getting rid of Docker from the container. And I don't know. I know you love Docker, but I don't know. What's the future like for Kubernetes and then in partnership with Docker? And then second question is the customization in the Kubernetes world. What is their position? And then how would you guys like to run with a customization team, or there's a separate organization or whatever? Yeah, thank you.
On Docker, I'm going to answer this question very seriously. There's a lot of confusion about the relationship between the Kubernetes project and Docker. There's further confusion about the difference between Docker, the company, and Docker Desktop, the tool. That is bad naming that we're going to pay for until we die. Okay? But Docker, the company, and Docker Desktop, the tool, are very different things. So there was drama over us deprecating the Docker shim. Docker, the entire tech stack, was the original runtime for the Kubernetes project. Eventually, that was no longer true. We introduced standards on how runtimes had to interact with the kubelet, and Docker did not comply with that. So we required a little software shim to get at the instance of containerd running inside of the Docker tech stack for people who didn't want to run containerd directly because they'd been around since the dawn of time and they were used to running Docker because it used to be the only runtime we had. But that thing was a pain to maintain, and we didn't want to maintain it anymore. It was a security issue. We were having trouble getting people to maintain it. It's not great. So we got rid of the shim. And now you can't run Docker, the entire tech stack, as your runtime. You have to run Cryo or Containerd or whatever your runtime of choice is directly. But that doesn't mean we're like getting rid of Docker. What Docker produces is an OCI compliant container image. You can still use Docker in development. You can still use Docker anywhere else you were using Docker. You just can't use it as your entire container runtime anymore. You can still use it as a development tool to produce container images that Kubernetes will run just fine because it doesn't care. It's producing an OCI compliant image. Same as Podman does, which is now a CNCF project, which feels weird, but whatever. So we didn't kill Docker. I really like Docker. You just can't use it as your whole runtime anymore, unless you're using like a super old version of Kubernetes, and I deeply wish you would not. Because we did kill that in like 1.23. For your second question on customization, like because we are an open source project, we do not care what you do once you are running it. Have fun. If you produce something that's like cool and useful and you think is like more broadly useful than your specific org or your specific team, we would love to see it contributed back. Sometimes that may be like a code contribution to an aspect of Kubernetes, and sometimes it spins off into its own sub-project or its own CNCF project sometimes. As you see, we've got a bajillion of them. But yeah, like we love it when people do weird stuff with Kubernetes. Please do. Make it solve weirder, harder problems in a weird, hard way.
Great.
Yeah. All right. Thank you, everybody.
Next up, we're going to